Hello everybody. This is going to be our topic 6 video on the Compton Effect, and I'm going to hop right in with just a little bit of a review of the historical context of the early 20th century, because that's really, this is where physics kind of meets social studies, and hopefully you find this kind of cool and fascinating. You need to know what scientists did and what they knew at the time and what they were trying to accomplish, what experiments they did, what theories they had. If I haven't made this clear in class, it's actually going to likely be a part of your diploma, is knowing who did what and when. Maybe not the date specifically, but you need to know kind of the rough idea as to what occurred. So a bit of context before we begin with the Compton Effect. In the early 20th century, scientists were grappling with a problem as to something called the ultraviolet catastrophe. To be honest, I'm not sure that we even really have a conclusive answer to this problem yet. But here's the puzzle, is that when they heated up objects that were black bodies would absorb radiation, right? And that's what makes them black, is that black absorbs all color of the spectrum, white reflects all color of the spectrum, blue reflects blue light, and absorbs the rest. Red reflects red light, but absorbs the rest. So black is supposed to absorb all colors, but as it absorbs all of these frequencies, what it's supposed to do is it's supposed to start vibrating, it's supposed to heat up basically, and it starts to glow different colors. And the first color you see something glow is red. And that's because red is the longest wavelength. It's also the first color that you see when you say heat up something, like say you're on your stove, right? If you have an element on your stove, it's going to glow red first. Eventually something might heat up enough to start glowing yellow and then blue, and then after a while it starts to glow white. And the reason why it glows white is that now that's the recombination of a whole bunch of colors, and we know that white light is really all the spectrum colors put together. And so once it gets to a certain point, you're actually starting to see all of these colors merged back into white light, and there's the phrase white hot, which is basically about as hot as something can end up being. The question though was, well, hang on, that's not true. Why can't we just heat it up more and more? Why can't we heat it up and so that eventually after red, orange, yellow, green, blue, violet, why can't we give off ultraviolet? Why can't we give off, for example, why can't we give off X-rays or gamma rays or something else along those lines? And that didn't happen, and that perplexed scientists. And so at the turn of the 20th century, a guy named Max Planck suggests something. He suggests that maybe all frequencies aren't possible. He suggests that maybe energy is quantized, and that energy comes in discrete energy packets. The staircase analogy is a good one, where before that they used to think that, well, you could have half of a unit of energy. And what Max Planck suggests is that maybe you can't have half a unit of energy. Maybe it literally comes in discrete values. And he suggests his constant 6.63 times 10 to the minus 34, and suggests a new formula, E equals hf, which hopefully you're familiar with. 5 years later, Albert Einstein coins the term a photon, and basically he suggests that, well, maybe light, which is as we know is a form of energy, maybe light as a form of energy comes in particles, photons again. And that's kind of where we're going to pick up our history lesson here, is the idea that I've got listed here, that maybe scientists, well, no, not maybe, scientists were re-examining some of their ideas about how EMR really worked. Because for the longest time, they thought that light was clearly a wave. There was clear evidence light was a wave. It could diffract, it could refract, it could interfere with itself. Young's double slit experiment in the year 1801 seemed to conclusively prove that light was a wave. Now, the double slit experiment is on its own kind of a unique, strange phenomenon, where when you shoot two rays of light, you would expect to get a pattern of two things, but you don't. You actually get this interference pattern. Now, although that does seem strange to some people, it actually could be explained using classical physics. But this quantum physics that we're about to head into, it goes back to resuggesting that maybe light is back to being a particle, that photon of light. And that's where we're going to work with right here. Based on Einstein's work, physicists predicted that a photon, which is like a particle again, right? A photon would be a particle of light. It should have a momentum. That's what their theory was. Anything else that's a particle should have a momentum. So the question was, could they prove this? And they eventually put together a formula to derive this momentum, right? And so here are the two formulas. It's either P equals h over wavelength or P equals hf over speed of light. You'll recall that the formula V equals frequency times wavelength. that basically v being c, the speed of light. That's basically the link between these two. They managed to derive an equation, and this is where theoretical and experimental physicists kind of come in. Theoretical physicists on paper make equations, but they had to prove it experimentally, and that's where A.H. Compton came in. We're going to talk about that in a sec. First, I want to show you where the formulas came from. First, we believe that photons are clumps of energy, but we also believe that they have momentum because we believe that they're particles. So we're going to take two equations. We're going to take the first equation, P equals mv, which we learned in our first unit, the momentum unit. Momentum is mass times velocity. But the problem is, how do you find the mass of a particle of light? I mean, physicists do believe that there is a resting mass of light. I've read it somewhere in an article. We're not really focusing on that here, but physicists believe that I guess there would be a mass to this. But maybe a better way of approaching it is using Albert Einstein's famous equation E equals mc squared, which suggests that energy and mass are interrelated. Now, we're going to talk about this unit in our final unit, which is really all about quantum physics. We're kind of leading our way into it with this third unit on EMR. But in our next unit, we're going to talk about this equation some more. His famous classic equation, you probably all heard it, E equals mc squared. So for right now, just go with that equation if you could. We'll get to Einstein's bit of it later. And basically you can see I've rearranged it for mass, right? So mass will be how much energy you have divided by the speed of light. Well, therefore, we're going to substitute that into this formula here and say momentum is energy over the speed of light times the velocity. But wait, we know that the speed of light is the velocity of these things that have energy, right? Because isn't the speed of any electromagnetic wave the speed of light? So v really is c, which kind of means that you can then cancel the squared with the velocity there, because those are the same things, and it leaves you with the formula is that momentum is equal to your energy divided by the speed of light. Now, we also know that energy, according to Planck, is equal to hf, or hc over wavelength. So by doing one more step, you could then put hf up here in for E, and that's where you get momentum is equal to hf over c. Or, since we know there's that relationship between the speed of light, frequency, and wavelength, you can make the second formula. And so here are two formulas that should be on your formula sheet that then should calculate for us the momentum of a photon I mean, we usually say photon of light, but in theory, radio waves, microwaves, X-rays, they all are photons. They're coming in packets. And so one of the ways that we sometimes try to draw that is this would be a wave. You may end up seeing this kind of picture before where there's like an oval with like a wave inside of it, kind of indicating that there is a wavelength that comes in a certain packet of light, and this is your photon. That's one of the ways that I might end up drawing that. So back to our story. So scientists theorize that maybe things have a wavelength to it. Now keep in mind, this is actually after the photoelectric effect. And so Robert Millikan has done his photoelectric effect experiment. We've also proven that a charge is a 1.6 times 10 to the minus 19. And we're 20 years later. And so we're now up to the year 1923. And in 1923, a couple of important things happen. A.H. Compton starts experimenting by shooting high-frequency X-rays into different materials. And this is what he was expecting. Now, this is based on the wave model again, but he expects that if you were to shoot a wave into a piece of metal, graphite, which is basically carbon, right? Graphite, carbon. You should have long X-rays, and what should happen is as you shoot them into there, that they would be compressed. I mean, isn't that kind of what happens when you shoot light into perhaps a different medium, is that, perhaps these are going to get compressed. That would seem kind of likely. But I got to scroll down so you can see the rest here. However, Compton discovered that the X-rays not only did not compress, but they scattered. And when they scattered, they actually got a longer wavelength. They didn't actually compress. You would think that if you hit something up against a wall, it would squish, right? Does that not seem kind of logical? But what ended up happening is it actually had a lower energy amount. And so this next picture describes what actually happened. Compton discovered that electrons were actually getting thrown off at an angle. And so, first of all, the wave was coming in like this. And then second of all, there was an electron getting kicked off to the side at an angle. And then thirdly, the scattered X-rays were actually longer than they were beforehand. They weren't compressed, they were actually longer than beforehand. So I'm going to scroll down so you can read the last little bit. Sorry, there's a bit of a page break in the way. But using conservation of energy and conservation of momentum and photon theories of light, Compton was able to eventually explain his results, and as always, it was named after him. It was called the Compton Effect. And he was eventually able to perfectly predict how the wavelengths would change, as well as figure out where these electrons were going to go. And if I could, I'd like to discuss how this is really similar to the photoelectric effect, though, right? Wasn't the photoelectric effect the idea that a wave of light would come in, it would hit a surface, and it would eject an electron? I use the analogy of a bowling alley at some point, where if this has enough energy, if these waves have enough energy, what's going to happen is that they're going to be able to knock the bowling pin out, and through the process of doing work, you're going to eject the electrons. Well, this is similar, except rather than it being a work function, what ends up happening is the wavelength that phases through. Now, it phases off at an angle, and it loses energy, right? This would have had an energy that is high. I'll use a high, an up arrow. These had high energy. I mean, they're X-rays, right? X-rays have a high amount of energy. Well, what ends up happening is the energy right here went down a little bit, right? And we have longer wavelengths, and so they've lost some energy due to a longer wavelength. But the reason why is that the missing energy, he was able to then calculate where the missing energy was. At first he thought, well, how are we losing energy, right? Is it due to the work function? But actually, in this case, it was due to an electron. And this electron is getting kicked off with kinetic energy, which can be calculated with 1/2 mv squared, which is basically very similar to what we discovered in the photoelectric effect. And what this ended up doing was it led some scientists to start considering the idea, and hopefully you can see this at the bottom of the page here, of wave-particle duality. This is going to be the subject of our last lesson. And it's where scientists started to finally realize that at the quantum level, which is really the subatomic level, that things behave differently. That particles sometimes behave as waves, but they also behave as particles. And you can actually think of this wave right here as behaving as both, because it's behaving as a wave because it has a measured wavelength. We can actually measure its wavelength. But at the same time, it's behaving as a particle because when that photon of light came in here and passed through the graphene, it found an electron to hit, and it collided with it like the bowling pin analogy. But I mean, it didn't just stay as a photon and just disintegrate and turn into nothing. As soon as it was done being its photon of particleness, if that makes sense at all, that particle property of it, it went back to being a wave again. And so it's almost like it just temporarily transformed into a particle, hit an electron, and then went back to being a wave. It's like this was like the best escape vehicle in the world. This is like the perfect crime. I'm going to be a wave for a while. No one will see me. And then, oh, now I'll be a particle. I'm going to hit this guy. Oh, now I'm back to being a wave. No one can see me again, right? Like it's like first I'm a particle, or first I'm a wave, then I'm a particle, then I'm a wave again. And yeah, scientists started to realize that the answer to the question, is light a wave or a particle, they realized the answer to that question is yes, it is both. And I've got some cool videos we're going to show you, and we're going to talk about this in our last topic on wave-particle duality. But for right now, let's spend more time on the Compton effect. So here's another picture kind of illustrating the concept. Light's coming in as a wave. And then all of a sudden, for a brief moment in time, it acts as a particle, because that particle, with momentum principles, hits the electron goes one way, the particle goes the other way, only it ceases to be a particle, it turns back into a wave, right? Haven't we done this question before? Literally on like the first or second day of the semester, where we have a particle comes in, something with matter comes in, hits a stationary object, one object goes one way, the other object goes the other direction here. This is a classic momentum concept, but momentum would imply that you have particles with mass. Particles, right? And like I said, for a brief moment in time, this thing turned into a photon, and then it turned back into a wave, right? It seemed to do both. So that's what we're talking about in this next little bit here. If EMR acts truly as we believe, as a particle, then it should have momentum, and we can calculate its momentum just like we did back in the first unit. Now, any electron can be calculated using the formula P equals mv, because we know the mass of an electron now. It was discovered. It took until 1909 when the Millikan oil drop experiment helped prove charge, because once charge was discovered, they could then calculate mass. So anyways, momentum of electrons can be calculated this way, but using the theory they had come up with earlier in the 20th century, they also had a way to calculate the momentum of an X-ray. believing that even though it's behaving as a wave, it technically also is a particle as well. So now we have two formulas we need to use simultaneously to calculate momentum. And we're more or less going to redo momentum from Unit 1, which is actually one of the reasons why I made this a YouTube video, is that this is really back to heavy math calculations. Now, I don't know where, but somewhere on your diploma exam, you're probably going to be given a two-dimensional vector problem. And that's what this really is. This is a two-dimensional vector problem, because you're going to have, in a way, a blue triangle right here, where there is going to be a y and x component. And you're also going to have a green triangle right here, which is also going to have an x and a y component. And the only reason why you have those triangles is because on the way in, you had a red component, and red was just purely in the x direction. And it's this sort of splitting problem. We should have done a lab on this with pool balls even, where we had a glancing collision. That's really what's happening. But what's different about it, though, is that there's different scenarios taking place. Here you have wavelengths, here you have a particle, and here you have a wavelength again. And for a brief moment, your wavelength seemed to turn into a particle in order to crash into it, into the electron, but then it turns back into a wavelength. And the wavelength gets longer, not shorter like they predicted, but longer. This is going to be the smaller wavelength, and then the wavelength is going to increase. And if the wavelength increases, it means its frequency decreased. And if its frequency decreased, it means its energy decreased. And why did it lose energy? Well, because the remaining energy the electron now has. Now, A.H. Compton eventually figured out a formula for this. This is one of the few formulas that we haven't covered on your data sheet. And the nice thing about this particular formula is that it's fairly straightforward. It rarely links in like multiple steps, at least that I've ever seen before. There are some equations where you have to put 3 or 4 equations together, build your own formula. This one's a pretty standalone formula. It's known as the Compton formula. And here's what A.H. Compton discovered. He could measure the change in wavelength. Now, if I can go back a slide here, the wavelength right here, we know it is going to increase. So this could have been, say, 100 nanometers. Well, we know that at some point it's going to move up to, say, 120 nanometers. And the reason why is that it needs to lose energy. And if it loses energy, it loses frequency. And if it loses frequency, it gains wavelength. And so that's what this tells us. The change in wavelength is how much extra wavelength we're going to get. And it's really based on a whole bunch of constants and one variable. It involves Planck's constant. It involves the mass of the electron. This has to be an electron, by the way, this m right here. It needs to be the speed of light. And then it's 1 minus cosine theta. And theta is the only true variable. These numbers right here are constants because they never change. Mass, c, and h. These are all constants. We always know Planck's constant. We always know the mass of something. Because it's the mass of an electron, we always know the speed of light. So really the only variable that we need to worry about then is cosine of theta. And so theta stands for the scattered X-rays angle. You got to make sure you're aware of this. This is the angle of the X-ray. So right here, if I could go back up to this diagram, which I've drawn all over, there's 2 angles. There's going to be the angle of the electron getting bounced to the side, but the theta that we want to know is the theta between the standard trajectory that the photon should have gone on versus how it's moved here. This is where theta happens to be. It's for the photon itself. So now that we have that, let's try solving some questions, because that's basically the rest of my lesson here. So let's try a few. Let's say you have an X-ray with a wavelength of 1.28 to the minus 12 meters. We're going to shoot it at graphite. First, I'm going to draw a bit of a picture. So here is a wave. That wave is then going to turn into a particle. Draw it as a particle for a second. It's then going to hit an electron. The electron is going to bounce one direction here. And I'm going to use a new color here. What's going to end up happening is, compared to what would have been straight on, why don't I even use green as the upwards color here? Let's just make sure I use a whole bunch of different colors to keep it straight. So the electron is going to go this direction here. This is now my electron. However, my photon, which I kind of drew here in red, my photon right here is going to turn back into a wave, and it's going to scatter, but now it's going to have a longer wavelength. So it's a longer wavelength. And what I get to know is that the angle is 15 degrees. The initial wavelength was 1.28 times 10, that's an 8 times 10 to the minus 12, and that's really all we need. So step one, let's find the wavelength of the scattered X-ray. I know it's going to be longer than it originally was, so let's try our formula. The formula is that your change in wavelength is equal to, just remind myself, it's h over mc, which is really its momentum, by the way. mc is mass times velocity, it's its momentum. And then 1 minus cosine theta. So it will be 6.63 times 10 to the minus 34, divided by the mass of an electron, 911 times 10 to the minus 31. You might say, why the mass of an electron? Because the electron is the scattered momentum. The electron's the other particle that's moving. We need to know the speed of light, which is 3.00 times 10 to the 8, which is the speed that the photon would be traveling. And then finally, 1 minus cosine of 15 degrees. So this one's pretty straightforward. There's not a lot you need to do to this. So just type in some numbers and hopefully don't make any mistakes. 663 times 10 to the minus 34, which was discovered. Again, Robert Millikan had to discover the Planck's constant, or at least prove it and confirm it in 1916. We then need to divide by the mass of the electron, which, hey, again, Robert Millikan was able to help out with when he discovered his oil drop experiment, because it gave us the elementary charge, and then once you had the elementary charge, it then allowed us to calculate the mass of the electron. We also have to divide by the speed of light, which was only possible due to many contributions in history, specifically the Michelson experiment with the rotating wheel. That was really important. You can see why all this history is important here. You need to times that then by 1 minus cosine of 15, and make sure your calculator is in degrees, please. So here's what I got. A change in wavelength of 8.266, etc., times 10 to the minus 14 meters, which is our change in wavelength. Now, here's the point of the question. It said determine the wavelength of the scattered X-ray. Students always make this mistake. Well, hopefully they don't, because I teach them, hopefully, really specifically right here. We now know how the wavelength has changed. It used to be 1.28 times 10 to the minus 12. It didn't become 8.266 times 10 to the minus 14, because if it did, that means it got squished. That means that it used to have this wavelength, and if it becomes this new wavelength, it's now become squished. No, that's not the case. It did not become a smaller wavelength. It became larger. You have to add this on top of your original wavelength. So take your change in wavelength and add 1.28 times 10 to the minus 12. And you'll end up getting a new wavelength of 1.36266, etc., times 10 to the minus 12, which means that this thing used to be 1.28 to the minus 12. Oh, I guess I had it right here. It used to be 1.28 times 10 to the minus 12 meters, and now it's bumped up to 36. Now, when it comes to sig digs, we need to point something out. There's special rules for sig digs. If you can kind of imagine writing this number out, I won't write all the zeros, but imagine this was really 0.000008266. And what you'd been asked to do is add to it 0.000, let's see, I need one more zero, I think. Oh, I want to do that differently. Hang on, let me try that again. I want to start with my initial number. The first one used to be 0.000128. Okay, that would be the 128 number there, right? And what ends up happening is you want to add to that 0.00, I don't want to write all the zeros again, and then this would have a few more digits, and then you'd get your 8266. Okay. That's kind of how I want to illustrate it, is that there's a whole bunch of zeros for these numbers here. This was the minus 12 number, and this bottom one's to the minus 14. And what ends up happening for sig digs is you're always supposed to cut off at the least precision when you're adding them, which makes sense because although this is still going to be 3 sig digs when I'm done, some kids might look at this and say, Chris, you only got 15 degrees right here. And so with 15 degrees, that means you only get 2 sig digs. But that's really not how this works. This number right here, I guess, yeah, this number right here should only have 2 sig digs. But when you add it to the 128 number, hopefully you can kind of see that if you add 128 and you add 8 more, you end up getting 136. And that's kind of where this number comes from here. So if that hopefully makes enough sense to you, The idea is that you need to cut it off based on your limited precision when you're adding a change in wavelength. And so you're going to end up with 1.36 times 10 to the minus 12 still. Because otherwise what would end up happening is you would have been at 1.28 times 10 to the minus 12. And then your new number would become 1.4 times 10 to the minus 12. And we can be a little bit more exact than that based on how we're adding these numbers to each other. We know that we're not actually that close to 1.4 because we know the number that we added was this little tiny amount right here. And so I can be a little more specific. It's not 1.4. I don't have to round that generously. I can leave it at 136. So I left a little note there, by the way, if you didn't catch that. Remember your rules for sig-digs when adding. So if you need a little tutorial on sig-dig adding rules, can you check in with me and ask me a question on that? So, the second part of the question then is, well, what's the velocity of the ejected electron? And what really ends up happening here is a very classic splitting question. I'm gonna draw this. There's one that goes up like this. There's one that goes down like this. And so I have now calculated that the initial wavelength was 1.28 times 10 to the minus 12. And my final wavelength is now 1.36 times 10 to the minus 12. And those are wavelengths. What we'd like to now do is calculate what the velocity of the electron is, because these are waves here. Let me draw that with a wave. This is now a longer wave, but we want to know what the electron's velocity is. And this is just a classic momentum question. So one of the ways that you can do this is just kind of break it up into its x and y components. There's going to be an x and y component to your electron, but there's also going to be an x and y component to your wave. And so I'm going to calculate the momentum. The formula for momentum, if you want to go back a little ways here, we calculated momentum was P equals h over wavelength. So what I can say is right here is the momentum at this point will be h over wavelength, which means I can take 6.63 times 10 to the minus 34 and divide by 1.28 times 10 to the minus 12 and calculate a momentum right here of 5.17, etc., times 10 to the minus 22. And I'm going to store that as letter A. And so I now have the momentum incoming. The amount of momentum that the incoming wave was A. Now, over here, I'm going to have to write this really neatly. We have to do the exact same thing. I have to take the momentum on the hypotenuse, and I have to basically take Planck's constant, divide by the wavelength to get that value. But I don't actually really care about the hypotenuse amount. I care about the x and y components. So I'm going to try to draw this as neatly as I can, but I'm going to make this be letter B and this side here be letter C. And the way I'm going to calculate that is I'm going to take Planck's constant, so 6.63 times 10 to the minus 34, and I'm going to divide by 1.36 times 10 to the minus 12, which is going to give me a value of 4.875, give or take. I'll do decimals, times 10 to the minus 22. And that's going to be your momentum on the hypotenuse. But you're going to need to times that by sine of 15 degrees in order to get letter C. And you're going to have to times 4.875 times 10 to the minus 22 multiplied by cosine of 15 degrees to get letter B. Right? Because B is going to be your adjacent, C is going to be your opposite. And don't forget that angle in there was 15 degrees. So just give me a second to try to find those numbers, and I'm going to store them in my calculator. So if I times this by, let's do sine of 15 first, I end up getting 1.26 times 10 to the minus 22, and we're going to store that as C. And if I go back up and I take that 4.875 number and I times by the cosine of 15 degrees, I end up getting 4.708, etc., times 10 to the minus 22, and I'm going to store that as letter B. So B was basically h over wavelength cos theta, and C is h over wavelength sine theta. Okay, so I have those saved now. The next thing I'd like to do is keep in mind my vector sums. A is how much it's coming in with. C and B are right here. I can now calculate what, say, D and E are going to need to be. Right? Because D, in this particular example here, will be whatever side B and A are subtracted from each other. If I can go write some more steps here. D is going to be equal to A minus B. Because A is how much incoming momentum we had, and B is how much X momentum you had right here. And so to do that, I'm just going to take letter A and minus letter B. And when I subtract those, I ended up getting, I'm going to store it as letter D. Store as D. I got 4.70 times 10 to the minus 23. Now that is my X component. I might even put a little note on that. So this is in the X direction. But I also need to know my Y directional amount. But in the Y direction, there was no incoming Y momentum. So that means that whatever I picked for C should be the same as E. So really C is E. And so what was C again? C was 1.26 times 10 to the minus 22. And so then for our last step here, we just need to re-put that together in a Pythagoras' theorem. And so E was this number here, and D was this number here. So I'm just going to square them and square root the whole thing, right? So it'll be D squared plus E squared square rooted. That'll give me my hypotenuse. So D squared plus E squared square rooted. And I got a final value of, let's see, my momentum. I have a final value of 1.3467 times 10 to the minus 22. Now that's its momentum, but we were actually asked to calculate the velocity. So the last thing I got to point out is that its momentum is equal to mass times velocity. And that's because it's a particle, right? This was an electron. This is the momentum of an electron that was ejected, right? This is basically the photoelectric effect in a different sort of way. So all we have to do then is divide by the mass of an electron, which means we have to divide by 9.11 times 10 to the minus 31. Divide by 9.11 times 10 to the minus 31. And I got this final answer here. I'm going to finally use some sig digs. I'm going to make it 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters per second. Yeah, because it's 1.47, 1.48. 1, 2, 3, 4, 5, 6, 7, 8. Which is good, by the way, because this should come in lower than the speed of light. A good rule of thumb is don't make sure it's not greater than 3 times 10 to the 8 meters per second, because that wouldn't work. So there we go. Now we've solved for the velocity of the ejected electron. Technically, we should also find this angle right here. And so to find this angle right here, if I can make a little bit more room to work with, I need to tan inverse, let's see, E over D. So this is why I like to save values in your calculator, right? Tan inverse E over D. And I got 70 degrees, basically. Which means that this thing was scattered off at 70 degrees. And there we go. We're done. Now, that is the long way of solving this problem. There is a shorter way. If you know how, you could have treated it like this. This would have been your full incoming wave. And downwards at a 15-degree angle was your other wave. So I'll draw this as a wave. And then I'll draw another wave like this. But then your electron was going back up. This is your electron. You can use the cosine law if you know how. And so I'm going to try that real quick, because the momentum of these I still have written down. The momentum of the incoming wave was 517 to the minus 22. It looks like I have written. This guy was 517 times 10 to the minus 22. And I wrote down here that the wave that was going down at the angle was 4.875 to the minus 22. So this could be 4.875 to the minus 22. So if I'd like to, I could solve for this using cosine law. C squared equals A squared plus B squared minus 2AB cosine C. And so if you know how to do that, I'm going to give that a try real quick. I'm just going to make this be A and A. I'll make that be B and B. 15 15 degrees will be C, and this should work. So 4.875. I mean, it might not be perfect because I'm kind of skipping sig digs. I'm doing a poor job of that, to be honest. Okay, so I cosine lawed all of this, and hopefully I get the same answer as I had before. I have 1.34 times 10 to the minus 22. What did I get last time? 1.34? Yeah, here it is. 1.34 times 10 to the minus 22. My sig digs are a little off because I've been a little lazy in keeping track. You should always use exact numbers in your calculator. But, yeah, there we go. I've now managed to calculate for this side right here. Now, the downside is that if you want to calculate the angle, you have to use the sine law. But if you do want to just calculate just the momentum, keep in mind that's just the momentum of side C, which is really the side of the electron. I've calculated that value. And I guess that would be kilogram meters per second, because that's momentum unit. So there's an alternate way of doing that. Okay, that's actually it. I'm going to show you just the slide of our last topic. Topic 7 is basically what's going to lead us into our final unit, which is on quantum physics. It's atomic physics. And we're now going to start talking about wave-particle duality. The idea that light is both a wave and a particle at the same time. And so this was also in the year 1924, 1923, where, if I can just do a quick recap, Compton basically discovers this. I'll use this one as a principle here. He discovers that if he shoots a wavelength with high energy, it had to be high energy, so it was X-rays. He shoots high energy rays, they act as waves until it hits the target. And as soon as it hits the free electron, it acts as a particle, so it's back to being a particle. Well, it shoots the electron off in one direction, just like you'd expect matter to do, but then it ceases to be a particle and it goes back to being a wave. So I gave that silly analogy of like a criminal or a thief on an escape plan, right? Where it goes out and it hits somebody and then it takes off the other direction, it disappears again. It was a wave, becomes a particle just long enough to hit somebody, and then turns back into a wave again. And so if you look for it as a particle, it's not. Now, one of the cool things, if I can finish off this lesson, is hopefully I've shown you this idea back here. I forgot to mention it earlier. But hopefully I've shown you the idea that a photon has momentum. And the example that I like to do is shooting a flash camera at a symbol, like you'd see out of like a music room. And if you shoot a high enough flash at a camera, those photons will actually hit they'll hit the symbol out of the camera, and you can actually hear the symbol resonate due to momentum. And we know that kind of makes sense because light's not acting as a wave there anymore; it's acting as a photon, and it's bouncing off. And you might even see the reflection again. It went as light, it hits the symbol with photon properties, with particle properties, and then it bounces off again as though it's a light wave again. It's really cool. And so, like I said, this is where we're going to be continuing our transition out of classical physics and into the realm of quantum physics. So that's about all I've got for our lesson. It's actually fairly straightforward. The hardest part really is to be able to do the momentum part. So I've reminded you how to do the momentum section with all of these diagrams right here, where this is a good one right here, where it comes in and then if this was its original trajectory, it splits in two different directions. You need to be able to solve one of those. And so if you're still struggling on that momentum concept, call me over and have me help. Otherwise, I'm going to wrap things up. That's the end of our video. So thanks everybody for watching, and we'll chat soon.